Alright, so let's start with example 7 here. The graph at right shows the velocity. It's important to note what you're even talking about. Alright, so we have the graph of velocity here. We're asking when's the particle moving down, when's the particle moving up? Well, let's see, when velocity is greater than 0 or positive, that's when you're moving up. When velocity is negative, that's when you're moving down. Alright, so when velocity is positive, that would be right here from, when is the particle moving down? Well, the velocity is negative here, so the particle's moving down from 0 to 1. Alright, and then when else? Well, let's see, it's negative, it's negative, it's negative, and here again, on this part, velocity is positive here, but what's this value? Okay, there's problems like this all the time where you want to just assume that it's 4. No, well, you can't assume that. You have to really figure out what it is. Alright, so we know that this point down here is 3, negative 3. We know that this point up here is 5, 2. So we could figure out where that's crossing the x-axis. Alright, so let's see. We first figure out our slope. That'd be 2 plus 3 over 5 minus 3. So our slope is 5/2. So the equation of our line, alright, y equals 2 plus 5/2 times, oops, that's 5/2 times x minus 5. Alright, and we're trying to figure out when is that 0. Right? And everybody hates fractions, of course, right? So I'll just multiply everything by 2 here, because if I multiply 0 by 2, it doesn't change it. Alright, and distributing that out, I get 5x minus 25. Alright, solving that. So 0 equals 5x minus 21. Okay, 21/5. Or if you feel like writing it as a decimal, which you can, 4.2. So don't say 4 or about 4. It's at 4.2. So when's the particle moving down? Oh, well, I did this back. I wrote this in the wrong spot. Let me just move it here. Alright, so this one should be, when's the particle moving up? Because the velocity is positive. Alright, and then we have this as well. Let me get back to my pen. Alright, so this is from 4.2 all the way to a t-value of 5. Alright, so if it's moving up here and here, alright, and what about this end? It's actually still positive there, so we should change this to a 6. So it's moving up from 4.2 to 6, and at 6, it doesn't matter if it's closed or open in this case. When's the particle moving down? Well, when is the velocity negative? And that's from 1 to 4.2. 1 to 4.2. Alright, when does the particle reverse direction? Well, when does it change from moving up to moving down? It's right when it crosses the y-axis here. So that's at those specific points. So at t equals 1 and at t equals 4.2, or again, if you feel like it, use 21/2. And when's the particle moving at a constant speed? Alright, it looks like the only constant part of our graph would be from 5 to 6. When's the particle moving at its greatest speed? Well, remember speed is the absolute value. Oh, let me write, the speed is the absolute value of velocity. So let's see, if I was going to draw the speed graph, I could just kind of reflect this up here because it's absolute value. Alright, and somewhere up here and down. So it's not quite symmetrical, okay? I should have more of a turn here. But the highest speed, where is it furthest from the x-axis? Well, the speed's 2 here, speed's 1, 0, okay? then 1 in the opposite direction, 2 in the opposite direction, 3. It looks like the highest number that we reach is -3, but with speed, remember, it's just positive. So when is the particle moving at its greatest speed? At t = 3. It's moving at 3 meters per second there. So that's the fastest speed that it gets to. When is speed increasing? All right, so this is when we're talking about when the velocity, if the velocity is positive and acceleration is positive, okay, or slope, remember that's just v prime and t. So let's look at this. So we're looking for when our function is positive, and acceleration, that's talking about slope of derivative, slope of the velocity. So we're looking for where it's positive and increasing. All right. So that would be, in our case, looks like the only spot where it's positive and increasing would be from 4.2 up to 5. All right, 4.2 to 5. And that's because our function is positive and the slope is increasing. Velocity and acceleration have the same signs. All right, and then we also have where is our function decreasing, okay, and the slope would be negative there. So where is our function negative and decreasing? So it looks like it's negative, it's decreasing here. Can we take a derivative at that point? No, that looks like a corner. So make sure that you're spacing out those two intervals. So from t = 1 to 2 and 2 to 3, it's negative and decreasing. The slope is also negative there. So when velocity and acceleration have the same sign, that's when speed is increasing. All right, if we do when is speed decreasing? Okay, when we're talking about decreasing, they have opposite signs. So we're looking for where our function is positive and decreasing, or where our function is negative and increasing. Oops, increasing. All right, and we have a few of those values. It's positive and decreasing from 0 to 1. All right, and it's also negative and increasing from 3 to 4.2. So because the function is increasing, our slope is positive, okay, our function's negative, the signs are different, so that's why it is decreasing. It's going towards the original value, the x-axis, all right? Graph the acceleration. Well, that's just the slope, where it's defined, all right? That's the slope of our velocity function. So it looks like on this line here, if we count rise over run or use the points, it looks like slope is -2. On this part, slope is -1. All right, right up here, slope is, I believe that's 5/2, right? We already found that. And here the slope is 0. All right, so now we just need to graph those values. So remember, acceleration is the slope of the velocity function. So from 0 to 1, it's -2. And we have a corner there, so that it's not differentiable. All right, from 1 to, oh, that should have went all the way to 2. Sorry about that. Okay, and then from 2 to 3, our slope changes. From 3 to 4, 3 all the way to 5, our slope is 5/2, or 2.5. So maybe about up here, 3 to 5. And then at the end, it's not moving anywhere, so it's not accelerating. And we have our graph of acceleration here. So we take a look, when is the acceleration the greatest? Well, where's it furthest from the x-axis? And it looks like it's in between the times from t = 3 seconds, oops, that's a 3. T = 3 seconds to t = 5 seconds. Okay. So let's move on here. we'll just probably work on this one, and we might have to talk about example 9 in class, because I don't know if I want you to watch too many videos this weekend. Alright, so on this gives us position. Okay, it's important to note what you're talking about. So we're going to estimate the velocity. Remember, the velocity is the slope of position. Alright, so at t equals 5 seconds, there's 3 options we have here for estimating the velocity or the slope of the derivative right there. Alright, we can say, we could do like s of 1 minus s of 0. We can look at those 2 points over 1 minus 0. Okay, so we can compare these, the slope here, or we could do s of half a second minus s of 0. So we could just look at the slope here. That would be a good estimate coming from that side. Or we could take a look between these two values. S of 1 minus s of 0.5 over 1 minus 0.5. Either of those would be a good estimate for right here. When it says estimate, alright, we don't have to get very exact. We're just estimating. So if you set up either of those, it would be perfectly fine. So you might do, for this one, 30.2 minus 40 over 1 minus 0. For this one, you'd do 35 minus 40 over 0.5 minus 0. Or you could also do 30.2 minus 35 over 1 minus 0.5. Alright, so for each of these, just show whatever you're going to set up. It doesn't matter which one you're doing. Okay, so for this one you could do, here's one option. You have 2 other ones, 38.2 minus 45. Because it's pretty close to 3. It's closer to 3 than it is 2, so maybe I choose to use this one. That should be a 45, okay? Over 3 minus 2.7. That is something that you could set up. And if you didn't want to figure out the actual value and you still wanted credit for this problem, just put the units. Okay, and that would be good enough right there. You don't need a number. Now, if you need to compare it to something else, you might need to get an estimate. Okay, type it into your calculator and use it. But for this, for what we're doing, you don't have to. Okay, and then 3.5, it doesn't matter. We could just do either of those 3 that I explained before. Alright, so this one I'm choosing to, oh, that's a 4. I'm choosing to use these 2 values. Okay, and again, you can just use these 2 or just use these 2. It doesn't matter. Just show the difference quotient that you're setting up. Alright, for the last part, I'm just going to mention some ideas. I want you to try it. Okay, talk to people, email me if you need to. Economics. See, Mr. Koff would love this because we're doing some economics and calculus. Marginal cost is loosely defined as the extra cost of producing one more unit. So if you have your function and you have a cost here, we're just looking at what it would cost, okay, the marginal cost that it would take to produce just one more unit. So if we add like 1 to our x value, and we add, it will go up a little bit or maybe down if our cost is decreasing. Right, so what we're really looking at is the derivative. Marginal cost is just the derivative of the cost function. Marginal revenue, derivative of the revenue function. Okay, and marginal profit is the derivative of the profit function. Alright, and then I want you to just try to go through some of these. Alright, when you see average cost, this is what we're talking about here. Find the cost for 10 radiators and just divide it by 10. And also, maybe if you want to save time, maybe you could put that into your y1 function. And maybe you could put this into your y2. We'll learn a little more about when to do that and everything later. Alright, what is the profit? You have to find the revenue and the cost and subtract them. Marginal cost, that's when we're using our derivative. Okay, and then this, you're using the values you already found, and then E, marginal revenue, using the derivative of revenue, and then just a question to answer. So you hang in there this weekend, you're almost done. We're getting to some really exciting stuff. Have a great weekend, guys.